Hello, everyone, and I hope you are having a good day. And today I want to continue talking about electrochemistry. Hopefully, remember that all redox reactions have electrons that go out of the oxidized species and into the species being reduced, right? And therefore, we can actually do something really interesting because all redox reactions follow that rule. See, hopefully you remember that the law of conservation of matter states that matter can't be created nor destroyed. So what we can do is we can use that law of conservation of matter to say that if 1 mole of electrons leaves the species being oxidized, one mole of electrons must also enter the species being reduced. Right? 1 mole of electrons leaves, 1 mole of electrons enters. So really what we can do is we can follow the path of electrons to balance out a redox reaction. And what we're going to be using is something called the half reaction method, in which each redox reaction is broken into 2 half reactions. And if we balance those 2 half reactions together, we should be getting a balanced whole reaction. Okay, so let's see how this works. Let's look at the reaction of potassium iodate plus sulfurous acid or hydrogen sulfate, leading to potassium iodide plus hydrogen sulfate. Okay, so just like we've been doing for these reactions, we're going to find the oxidation states of each species. So K is a +1, O is a -2 times 3. So there's 6 of those. +1 for K, I must be +5. H is going to be +1 times 2. O is -2 times 3. So we have 2 there, we have 6 there, -6 and 2. We need to add a 4. So S is +4. Is that right? Hold on, let me double check that. H plus 1. Oh, O is minus 2. That's 6. So that's 4. 4 to 6 and 6. Yeah, that makes sense. Plus, minus, got plus 1 times 2. O is minus 4, which is, oh, I'm sorry. O is minus 2 times 4. And S, that's minus 8, so S is plus 7 here. So then we got our two half reactions, right? And we can tell the half reactions by looking at what species is being reduced and which species is being oxidized. So let's start with the species being oxidized. And so we notice that K, not changing. O, not changing. But the I is changing and the S is also changing. So the S seems to be going, S goes from plus 4 to S plus 7. It's being oxidized, right? Now on the other side, our reduction half, we have our I plus 5 going into our I minus 1. So that's first. The next thing we're going to do is, this is all about electrochemistry, electrons. We're going to balance each half reaction by adding electrons to the appropriate place. So on the oxidation half, we have a plus 4 and a plus 7. We need to add electrons, but this is the tricky part. Because electrons are negative, we have to remember that when you add electrons, it negates, right? In other words, we need to add plus 3 electrons there, the oxidation side. Now on the reduction side, got to add it, make sure that we're always adding to the other half of the half reaction. In the oxidation side, we're always adding to the products. On the reduction half reaction, we're always adding to the reactants. And that works because there's a negative there, there's positive there. So we need to add 4 electrons there. Right? So right now we have our two balanced half reactions. We will notice that the oxidation half is giving out 4, but the reduction half, I'm sorry, the oxidation half is giving out 3. The reduction half is only taking in 4. They're not balanced together. And that's the whole point of writing the half reactions. These are not full half reactions. You have to balance the half reactions together so they have the same number of electrons in them. Because we know that for every 1 mole of electron going out, 1 mole of electron should be coming in. Whenever 1 mole of electron is given away by oxidation, 1 mole of electrons should be given in. So we can have a 3 and a 4, but that's an easy fix. We just multiply the half reaction by some number. And we're going to have 4 of the oxidation half reactions and 3 of them. Why? So then we have 12 total electrons. So our new oxidation half reaction is 4 S plus 4 going to 4 S plus 7 plus 12 electrons. Our new reduction half is 12 electrons plus 3 I plus 5, yielding 3 I minus. So now that those two are balanced, what we're going to do is we're going to use those two as our ratios in our whole reaction. So we see that in our oxidation half reaction, we have 4 S plus 4s. So there should be a 4, right? Ugh, I messed up my math. Oh my goodness. Oh my goodness gracious. No. No, I didn't. Oh, let's see how it works. Okay. 4 S plus 4s. So should be a 4 here. And then we also need 4 here. And then we should have 3 I plus 5s. So a 3 there. And we should have a 3 there. And theoretically, that should be balanced. Let's check it out. 16 O's there, 12, uh-oh, that's not balanced. Sorry about that. Let's try this again. Okay, so here are our oxidation half reactions, right? And we need to balance them by electrons, making sure that the electrons on one side of the reaction are equal to the electrons on the other side of the reaction. So we see that in our oxidation half, we have a +4 in the reactants and a +7 in the products. So I'm going to add 3 electrons right there, because that'll make a +4 on each side. On the reduction half, I have a -1 on the products. I have a +5 in the reactants. So I need to add 6 electrons over here. That way we have balanced by charge, okay? Now, what's happening, according to what we have seen, is that the oxidation half is giving out 3 electrons, but the reduction half is taking in 6 electrons. That's not good. Not good at all. Because, well, as we said before, every time 1 mole of electrons leaves, 1 mole of electrons has to enter. When 1 mole of electrons is leaving the oxidation species, 1 mole of electrons has to enter. So what we need to do is balance these two half reactions together. We have to balance out the number of electrons. So that's super easy to do. All we have to do is double up. So we're going to do that times 2. Right? So then our new oxidation half is 2s plus 4, yielding 2s plus 7 plus 6 electrons. All right. So then, now that our half reactions are balanced, we're going to take those values and we're going to pop them back into our equation up here. 6 minus 1. Yep. So here we go. According to this, we need 2 s plus 4s there. We also need 2 s plus 7s. And theoretically, they should be balanced. 4 and 4. Let's try this a third time. So messed up here. S is not +7. S over here is actually +6. So S should be +6 there. Okay. Let's write out our two half reactions again. Oxidation, reduction. Okay. Our oxidation half reaction. We have I is reducing, S is oxidizing. So we have S plus 4 turning into S plus 6. And then our reduction half, we have I plus 5 turning into I minus 1. Is that correct? Let's just double check. It's good. That looks good. That looks good. Okay. So now that we've written out our half reactions, we'll note that each of these half reactions aren't balanced, right? In this half reaction, if we look at the oxidation half reaction, this S is missing 4 electrons. This S is missing 6 electrons. So what we need to do next is balance each half reaction by number of electrons. So what we're going to do is we're going to add 2 electrons to that half. And then over here, we have to add 6 electrons. And that makes sense because the oxidation side is losing electrons, so it should be on the product side, whereas the reduction side is gaining electrons, so it should be on the reactants side, right? But the problem is that for each 1 mole of electrons being lost, 1 mole of electrons should be gained. According to our half reactions as written, 2 electrons are being lost, but somehow 6 are being gained. So now we have to make them into true half reactions by making sure the number of electrons are balanced on each side. Let's go ahead and do that. So that needs to be times 3. Okay. And then that's good. So then we're going to have 3s plus 4 yielding 3s plus 6 electrons. And now what we're going to do, now that our two half reactions are balanced, we're going to use these ratios up in here. So we got to throw in some 3s. So we should have 3 S plus 4s here. And we should also have 3 S plus 6s there. And now, if we look at it, we have 12 O's, 9 and 12 O's. We have 1 I and 1 I, 1 K and 1 K. We have 6 H's and 6 H's and 3 S's and 3 S's, all balanced. Okay. So let's quickly jot down what I did. Step 1 is I identified species being oxidized and reduced. Step 2, write out 2 half reactions. Step 3, balance individual half reactions by adding electrons. Step 4, balance number of electrons from each half reaction. And finally, use the balanced half reaction ratios in the whole reaction. Okay. Let's try one more for practice. We will have NH3 plus O2 yielding NO plus H2O. So have over here, we have H is going to be +1 because it's the lower electronegativity times 3. N is going to be therefore -3. O is all alone, so it's neutral. Okay, over here, O is -2 because it's the higher electronegativity over N. So that's +2, -2, +1 times 2. So we can see here, we have oxidation, we have reduction. So our oxidation half reaction, let's see, we have N going from -3 to +2. That sounds like oxidation to me. And -3 to N plus 2. And then reduction, we have O. Now, I'm going to do something funny. I'm going to write O2. The reason I'm writing O2 is because even though it's one O neutral, we know O can never be by itself. So I'm going to put O2 there, and then I'm going to have O minus 2. However, because there are 2 O's in this half reaction on the left, I'm going to balance out by mass on the right. So now let's go ahead and balance by electrons for each. So -3 on the left of the oxidation, +2 on the right of the oxidation. So I need to add 5 electrons. And then for reduction, we have 2 and -4. So I need 2 electrons there. Is that right? Nope, I need more than 2 electrons. I need 4 electrons because that's 2 -2s, which is a total of -4. So I need 4 electrons there. Okay, now we need to balance each half out. This will be times 4, and the reduction will be times 5. So our oxidation half, we have 4 n -3, yielding 4 n plus 2 plus 20 electrons. Right? And then over here, we're going to have 20 electrons plus 5 O2, yielding 10 O minus 2s. Okay, so let's start putting things in. I know that I need 4 N minus 3s. There. I also know that I need 4 N plus 2s. There. I know that I need 10 O neutrals or 5 O2s. There. I also know that I need 10 O minus 2s. I'm sorry, 20 O minus 2s. Nope, 10 O minus 2s. Yeah, right now we need 10 O minus 2s. Right now as written, I have 4 coming from the NO, which means that for this minus 2, I only need 6 more, because 6 and 2 is 10. I have to make that in blue, sorry. So that's how we balance by half reactions, right? So it's not the way you have to do it, but it is a very useful technique. Thank you so much for watching and have a good day. Bye.